Good afternoon, my dear students. So today in the sessions we are going to learn penalty approach method. According to examinations point of view, penalty approach method is most important. Okay. This is the first problem on the penalty approach method. So the figure, it is looking like a step bar in which the two end is rigidly fixed. Is it right? So in which first of all we need to determine the nodal displacement. So this means that we need to find out the value of Q1, Q2 and Q3. We need to find out in the nodal displacement, as well as we need to, in the second condition, in which we need to find out the stresses in each element. So this means that we need to find out the value of sigma 1 E1, sigma 2 E2. We need to find out in this problem, as well as we need to find out the reaction at this support. So we have three nodes: first node, second node and third node, in which we need to find out the value of R1. The normal reaction is acting at a point of 1, the normal reaction is acting at a point of 2, and the normal reaction is acting at a point of 3. R1, R2, R3. Okay dear, take Young's modulus for the steel, so and copper, as the modulus of elasticity of the copper is given as 100 gigapascal, and modulus of elasticity or Young's modulus of a steel is given as 200 gigapascal. Let us see this figure. This figure is looking like a step bar, the step bar in which the both end is rigidly fixed, as well as the load 100 kilonewton is acting the same direction of X. Okay, the diameter of the copper is 40 mm and the diameter of the steel is 60 mm. The length of the steel is 800 mm and the length of the copper is 500 mm. The first of all we need to find out the solutions. First of all we have to consider this first element for the steel and the second element for the copper. In the given data we have to represent here the element 1 for the steel. First of all we need to find out the area, because diameter is given. If it is diameter is given, then we have to use the formula A1 is equal to pi 1 d1 whole square by 4. So because we are discussing about which one here, we are discussing about the steel. For that reason we have to represent here area of the steel is equal to A1 is equal to pi d1 whole square by 4, you can say, otherwise pi ds square by 4. The meaning is should be remaining same. And pi into, what is the formula of area? Pi by 4 into d square. Pi as it is, pi by 4 into diameter of this steel, how much is given here? 60 mm whole square. So if you divide with the help of calci, then you will get the answer of 2827.43 mm square. The area of the steel, it is represented by A1 or AST. How much we got here? 2827.43 mm square. And the length of the first element, it is given as 800 mm, and the modulus of elasticity of the steel is given as 2 into 10 power of 5 Newton per mm square. Similarly here also the element of this copper. First of all, in which we need to find out the area of copper. Area of the copper, it is represented that ACU. If you want to find out the area, ACU is equal to pi by 4 into dt whole square. Pi by 4 as it is diameter of the copper, it is given as 40 whole square. If you divide this the whole the value, then you will get the answer of 1256.63. that is indicate that is the area of the copper. The length of the copper is how much is given? 500 mm is given, as well as the Young's modulus or modulus of elasticity of the copper is given as here how much? 2 into 10 power of 5 is given. Okay, so here clear. After that, the first of all we need to find out the step number 1. Step number 1. So let us see this figure. This is the first node, second node, and this is the third node. Okay, then the force here, the force F1 is acting at a point of 1, so we can say that nodal force is acting at a point of 1, and the nodal displacement also acting at a point of 1. F2 is indicate that nodal force is acting at a point of 2, the nodal displacement is acting at a point of 2, Q2. F3 is represent the nodal force is acting at a point of 3, Q3 is represent the nodal displacement is acting at a point of 3. So how many nodes we have here? We have 3 nodes, first node, second node, third node. The joining the first node to the second node, the forming of element E1, the joining the node from the second node to the third node, the forming of element is E2. So we can represent here first, second node, third node, element E1, E2. The length from first node to the second node, what we can say, L1. This is the L1 and this is the L2. Clear? After that, step 1 is completed. The step number 2, we know very well the element stiffness matrix. How many elements we have? 2 elements. This first element and second element. For that reason, first of all, we need to find out the first element. K1 is equal to A1 E1 by L1, 1 minus 1 minus 1 1. Okay, so let us see this figure. A1 E1, A1 E1. The area of steel, how much we got here? 2827.43, 2827.43. And then the modulus of elasticity or Young's modulus of the steel is given as 2 into 10 power of 5 by the length of the first element or length of the steel. How much is given? 800. 1 minus 1 minus 1 1. So if you divide this whole the value, then you will get the answer of 7.07 into 10 power of 5, 1 minus 1 minus 1 1. After that, 10 power of 5, if you multiply this term, 7.07 minus 0.7, 7.07 minus 0.707, 7.07. After getting the elemental stiffness matrix, we need to find out the elemental stiffness matrix for the second element. So K2 equal to A2 E2 by L2, 1 minus 1 minus 1 1. So this A2 is indicate that area of copper, and E2 is indicate the Young's modulus of the copper by length of the copper. So the modulus of elasticity or Young's modulus of copper, it is given as 1256.63, and E2 how much is that here? E2 is here, copper is given as 100. So dear, I did a small mistake here. Wait, here you have to represent not 2, this is the 1 value. How much? 1 into 10 power 5. Clear? So same thing we have to represent here. This is E2 is the modulus of elasticity or Young's modulus is 1 into 10 power of 5 by the length of the copper is given as 500, 1 minus 1 minus 1 1. Again, if you divide this the whole the value with the help of calculus, then you will get the answer is 2.513 into 10 power of 5, 1 minus 1 minus 1 1. Okay, 10 power of 5 as it is, just you need to multiply the term 2.513 into 1, 2.513, 2.513 into minus 1 minus 2.513 minus 2.513. Again here also 2 plus 513. Just you need to multiply this term into the whole bracket. After the getting the K1 K2, we need to find out the global stiffness matrix. We need to find out the value of K nothing but global stiffness matrix equal to elemental stiffness matrix of the first element plus elemental stiffness matrix for the second element. So K1 how much we got? 10 power of 5. This is how much we got K1 here? 7.07 minus 7.07 minus 7.07 plus 7.07. We got the value of K1 as well as we got the value of K2. We know the very well this K1, it lies in between the node is first and second, and first and second. This K2, it lies in between the node from second to third. Clear? After that, we have to arrange this node in the systematic order: first node, second node, and third node. First node, second node, and third node. So you know the procedure how to multiply. Again I will repeat. Just you need to multiply first node to the first node, then you will get the answer of 7.07. First node to second node minus 7.07. First node to the third node is available here? Not available. If it is not available, it will be considered as 0. Okay. Again, second node to the first node is minus 7.07. Second node to the second node is 7.07. Here also, second node to the second node is how much is there? 2.513. Again, second node is the third node is available here? Not available. If it, yeah, it is available. How much? Minus 2.513. Clear? After that, third node to the first node is available here? Here also not available. What about here? Here also not available. If it is not available, it will be considered as 0. Third node to the second node is minus 2.513. Third node to the third node is 2.513. Clear? After that, this is the first node, second node, third node, first, second, third. So 7.07, 7.070 minus 7.07. Just if you add this value, then you will get the answer of 9.583 minus 2.513, minus 2.513, 2.513. After that, our main intention is we want to find out the nodal displacement as well as we need to find out the nodal force we need to find out. So how many nodes we have? We have the 3 nodes. For that reason, the nodal displacement is represent the Q1, Q2, Q3, and the nodal force is F1, F2, F3. So generally we know very well the first end is fixed and the third end is fixed. For that reason, F1 value is 0 and F3 value is 0. The force is acting at the center point. That's what the value of the force is. How much? 100 into 10 power of 3. So after that, we need to find out the equilibrium equation for the given continuum. KQ equal to F. So K values already is given 10 power of 5, 7.07 minus 7.070 minus 7.07, 9.583 minus 2.513, minus 2.1513, 2.513. So that is the value of K. Q nothing but Q1, Q2, Q3, and F nothing but F1, F2, F3. Is it right? So we know very well. In this case, the node 1 and node 3 is fixed. If the node 1 and node 3 is fixed, after that we need to eliminate the first row, first column, third row, third column, first row, first column, third row, third column we need to neglect. So in which we have to select the penalty approach method, in which the fixed supports are modeled as a spring having the very large stiffness, element C. So in the penalty approach method, we are following the formula is C is equal to maximum Kij into 10 power of 4. That is the formula of penalty approach method. So if you observe this figure, which one is the maximum here? The maximum point is 9.583. How much? 9.583 into 10 power of 5. 10 power of 5, this is 10 power of 4 as it is. This is the formula. Okay dear. After that, if the bases are same, the power should be added. 5 plus 4 should be 9. So that is the value of C. That is the value of coefficient of stiffness matrix. Okay, or we can say as diagonal matrix we can say. After the getting the C value, just you need to replace in above 7 instead of 7.70, here also 7.70. Sorry, 2.513. We have to replace this value. Which one? 9.583 into 10 power of 9 here. Here also. Let us see here and here. 9.583 into 10 power of 4. Then again this value minus 7.070 minus 7.07, 9.583 is keep as it is only. Keep as it is only. Here Q1, Q2, Q3 equal to, this is F1, F2, F3. After that, we have to go for global force vector in the equilibrium condition. So global force vector F1 is indicate that F1 is equal to C is the coefficient of stiffness matrix C1 into A1, and this is F2 and F3 plus C A3. So this whole the value it is considered as F1 dash, this value considered as F2 dash, and this whole the value is considered as F3 dash. Okay, 0 and above 0, below 0 as it is. If you remove the 2 digit, it become as 10 power of 2. Okay, if the base is same, the power should be add, so we can say as 1 into 10 power of 5, 1 into 10 power of 5. Okay, so here the nodal displacement, because A1 is 0 and A3 are displacement are 0 because of it is a fixed end. A1 0, A3 0 because of it is a fixed end. Clear? After that, what we have to do? This is 10 power of 5 as it is. Okay, then 9.837 into 10 power of 4, just you need to multiply by Q1, minus 7.07 into Q2. Again this row into this column, not here, 0 into Q3 equal to 0. After that, this is 9.5837 into 10 power of 4 Q1 minus 7.07 into Q2. So this value become 0 equal to 0. If you divide the 0 by number, it should become, what will happen here? 0 only. So if this minus sign it's moved toward the right side, it will become as positive. Q1 is equal to 7.07 by 9.5837 into 10 power of 4. So you will get the value of Q1. Q1 is equal to how much? 7.377 into 10 power of 5 Q2. So in which we are not get the value of Q1 value. Again we have to go for the same similar process, same concept, 10 power of 5, this second row into this column. Okay, minus 7.07. Let us see, minus 7.07 into this Q1 plus 9.583 into Q2 minus 2.513 into Q3 equal to 100 into 10 power of 3. That is the second equation. Let us see, 100 into 10 power of 3. Minus 7.07 Q1 plus 9.583 as it is up to here as it is, 100 into 10 power of 3. Just you need to divide this value, then you will get the value of 1. So if you observe in this equation, okay, so minus 7.07 as it is, instead of Q1 we have to put this value. Q1 is how much? 7.377 into 10 power of minus 5 Q2. We can substitute here, plus 9.583 Q2 is unknown, we don't know, minus 2.513 Q3 equal to 1. After that, let us see in which term is common here. These both are common, just we have to add this value. Then you will get the answer of 9.5835 Q2 minus 2.513 Q3 equal to 1. So again we are not getting the answer. For that reason it is considered as equation number 2. Again the equation number 3, we need to follow the same concept, 10 power of 5 as it is, 0 into Q1 minus 2.513 into Q2 plus 9.5837 into 10 power of 4 into Q3 equal to 0. Let us see here, equal to 0. Clear? The same concept you need to follow here, minus 2.513 Q2 plus 9.58325 into 10 power of 4 Q3 equal to, just if you divide this value it will become as 0. Then again if this minus sign, if it is moved toward this side, means it become as positive. Then let us see, Q3 equal to 2.513, divide this constant value in the bottom of this side, 9.58325 into 10 power of 4. Okay, so if you divide the 2.513 by 9.58325 into 10 power of 4, then you will get the answer of 0.2622 into 10 power of minus 4 if it is moved above into Q2. So for that reason it is considered as equation number 3. After getting the equation number 3, we need to substitute in the equation number 2, then we will get the value of Q2. Let us see, 9.5835 Q2 minus 2.513 Q3 equal to 1. Then 9.5 0.835 Q2 minus 2.513. This Q3 value is how much is there? Plus 0.2622 into 10 power of minus 4 Q2 equal to 1. So after that, if you multiply this term, then you will get the answer of 6.589 into 10 power of minus 5 Q2 equal to 1. Then after that, so if we have to take this common here, Q2, here also Q2. If you subtract this value, if you subtract the value, then you will get the answer of Q2 is equal to how much? Q2 equal to 0.10434. After getting the Q2 value, we need to substitute in the equation number 1. So let us see the equation number 1 is Q1 is equal to 7.377 into 10 power of minus 5 Q2. 7.377 into 10 power of minus 5. Q2 value is 0.10434. If you multiply this term, then you will get the answer is 7.6978 into 10 power of minus 6 mm. So after getting the Q1 and Q2 value, then we need to substitute in the equation number 2. Then we will get the value of Q3. Q3 already we know very well here. Equation 3 here. We need to substitute Q1 and Q2 value. Then Q3 is equal to 0.2622 into 10 power of minus 4 Q2. 0.2622 into 10 power of minus 4. So what is the value of Q2 here? Just now we got the value is 0.10434. Okay, just a minute. So dear, I did a small mistake here. Please rectify them. Small value we will change here. Okay, I think so. The Q2 is how much we got? 0.10434 is there now. We have to substitute here. Just now I missed a small mistake there itself. Okay. Then after that, we got the value of Q1, Q2, Q3, that is the different one only. After that, getting the Q1, Q2, Q3, we need to find out the stress and strain. We need to find out. Strain formula is E1 is equal to B1 into Q. So B1 is formula we have 1 by L1 minus 1 Q1 Q2. So the length of the first element is given as 1 by 800 minus 1 1. So Q1 is 7.6978 into 10 power minus 6, 0.10434. That is a value of Q2. Okay. Then after that, if you multiply this term, minus 1 in this row into this column, minus 1 into 7.6978 into 10 power of minus 6 plus 1 into 0.10434. If you divide the whole divide with the help of calci, then you will get the answer of 1.30414 into 10 power of minus 4. So because we know very well strain is not having any unit, it's a dimensionless unit. Okay. After that, we need to follow the same concept here. The stress is equal to modulus of elasticity or Young's modulus into strain. Okay. So E1 dot E1. Okay, this capital E is indicate modulus of elasticity or Young's modulus. How much we got here? 2 into 10 power of 5 for the steel into the modulus of strain. How much we got here? 1.30414 into 10 power minus 4. If you multiply, then you will get the value of stress is 26.083 Newton per mm square. We got the value of stress of the strain of the steel. Again, we need to find out the strain and stress for the copper. We need to find out. Strain E2 is equal to B2 into Q, 1 by L2 minus 1 Q2 and Q3. 1 by length, L2 is how much? 500 minus 1 Q2 value is how much we got it here? 0.10434 and Q3 is 2.70. So dear, I did a small mistake there dear, because I think so it won't be get here that much. 2.736 into 10 power minus 6 I took. So whatever you are getting the answer here, just you write the same value only. Okay. After that, 1 by 500 as it is, just you have to multiply this row into this column, minus 1 into 0.10434 plus 1 into 2.736 into 10 power minus 6. If you divide with the help of calci, then you will get the answer of strain is minus 2.086 into 10 power of minus 4. After the getting the value of strain of the second element of the copper, again we need to find out the stress for the copper. We need to find out stress is equal to E2 into B2 into Q. So E2 as it is B2 into Q, what we can say, B2 into Q we can say as strain. Okay, so E2. So the modulus of elasticity of the copper is 1 into 10 power minus 5 into E2 value is how much is there, minus 2.086 into 10 power minus 4. If you multiply this term, then you will get the answer of the stress of the copper is minus 20.867 Newton per mm square. After the getting the value of sigma 1 E1, sigma 2 E2, then we need to find out the reaction at the support. First of all, we need to find out the reaction at the node, because of node 1 is the fixed end. Then which formula we have to use? R1 is equal to minus C Q1 minus of A1. Okay, minus C as it is. The Q1 A1 we can say as, we can represent as Q1 minus C. C is the maximum coefficient value. How much we got? That 0.583 into 10 power of 9. Q1 value is already we find 7.6978 into 10 power of minus 6. So if you multiply this term, then you will get the answer of minus 73768.01. After the getting the value of R1, we need to find out the reaction at the node 3. The same formula, node 3 also fixed. Is it right? R3, the normal reaction is acting at a point of 3. R3 is equal to minus C Q3 minus of A3. So Q3 minus A3, what we can say? We can say as Q3 only. So C is the maximum coefficient. How much already we got it here? 9.583 into 10 power of 9 as it is. Q3 value is 2.736 into 10 power of minus 6. Okay, so I hope so. I here 736, I put this value only. Okay, after that we need to multiply this term, then you will get the normal reaction value of R3 is how much? Minus 26219.088 Newton. After the getting the value of R1 and R3, you need to represent the result. The nodal displacement on Q1, how much we got? 7.6978 into 10 power minus 6. Q2 is 0.10434 mm. Q3 is 2.736 into 10 power minus 6 mm. Again, the stresses and strain value, how much stress we got here? 26.083, and stress for the copper we got as minus 20.867 Newton per mm square. And the reaction at the support, because this step bar is rigidly fixed from the both the side, so for that reason we need to find out the normal reaction, how much is acting at a point of 1 and how much normal reaction is acting at a point of 3. We need to find out. For that reason we have to follow the penalty approach method. R1 is equal to minus 73768.01 Newton. R3 is minus 26219.088 Newton. I hope so no one is having a doubt. Okay, please, if you have the small doubt regarding this session, please write down in the comment box, and please don't forget to subscribe my channel dear. Thank you.